We're going to start chapter 12 today. Totally different. We were doing configurations, electrons and all that. We're on to something. Now we're going to look at the states of matter. And the one that has the most variance is gases. So we're going to look at the characteristics that occur in gases. The weird thing about gases is if you take nitrogen gas and oxygen gas and hydrogen gas, they have the same characteristics as far as volume and pressure and when they have certain temperatures. It doesn't matter what gas you have. So there's some characteristics that are same and then some characteristics that are different. Okay? When you have a gas, it has an indefinite volume. Okay? It'll fill whatever container size it has. Like a liquid has a definite volume, a solid has a definite volume, gases don't. They can spread out as far as, the space that they have. If you're talking about, you can see in this picture here, if you're talking about at standard temperature and pressure, the volume of a gas is 22.4 liters. That's a standard, okay? But that's if you're at standard temperature and standard pressure, and we'll talk about those here in a minute. Okay? They have an indefinite shape. Again, they take the shape of their container. Okay? Liquids do that, but they have a definite volume. Okay? Solids have a definite shape and a definite volume. Okay? And they have very low densities. Okay? If you look here, water is 1 gram per milliliter. Liquid water, okay, is 1. That's its density. And your little air, 1.2. No, that's grams per liter. So that's 1,000 times less, okay? So when you're talking about densities of gases, because they like to spread out as far as possible, their particles aren't very close together. So their density is very, very, very low. Okay? They have high velocity. Their particles are moving really fast, and they have a lot of kinetic energy. Okay, kinetic energy can be measured with a thermometer, all right, because kinetic energy can be heat energy. So that's why when you take the temperature of a gas, it's higher. Over here, it's hard to read, and I'm sorry, I'm cutting it off, but it says volume occupied by 1 mole of water. This is water vapor. As a liquid, it's 18 milliliters. As a gas, it's 22.4 liters. Okay, so there's a huge difference if you want to look at that. So yep, if you have 1 mole of water and it's a liquid, you have 18 milliliters. Okay, but if you change it into a gas, now it's 22.4 liters. It's a huge difference as far as the volume. Okay, when you're looking at gases, we have things we look at. Pressure is one. Pressure is force per unit area. Okay, these little particles are banging against its surface. Here we got inside a balloon. Okay, and they move fast, so they're going to be banging and exerting pressure. Okay, so when you want to figure out the pressure, it's force per unit area or force divided by area. So if you had, when we're trying to find it, the pressure, there's some things we got to look at. First of all, we got to look at how many particles we have, because the more particles we have, the more force it's going to exert, because they're going to be moving around. They're all moving around fast, but if you have more in here, then they're going to be more collisions with the outside. Okay, temperature. As you increase the temperature, they move faster. If they move faster, then they exert more pressure. Okay. And the volume of the volume occupied by the gas, like this balloon. This is the volume of the gas. If I make the balloon bigger, then these guys aren't going to collide with the side as much because they got more area, more space. Okay, so the things that we look at when we're talking about gases, we look at how much gas particles and how many moles, the temperature, and the volume. Those are the things that can vary. Okay, the SI, the System International or the metric system unit of pressure can be a Pascal. It's weird because pressure, there's a whole bunch of them. Okay, there's a Pascal, which is 1 Newton meter. But you can convert it, okay? Atmospheres is usually what you'll see, okay? 1 atmosphere equals 760 millimeters of mercury. If you remember the old barometers where they used to measure, they used to use mercury. So these two equal each other, which also equals 760 torr, okay? If we want to do it into kilopascals, we can, 1 atmosphere equals 101.3 kilopascals, another unit that we can use. These are all pressure units. We have PSI, pounds per square inch. We have bars. These are all units, but they all equal each other. So if you have atmosphere and you need to change it to torr, you can just do a unit conversion, like we did with millimeters to meters and all that other stuff because they all equal each other. But the most common one we use is atmospheres. This one's common and this one's common. The rest of them, not so much. Okay. All right. So if I have 740 millimeters of mercury and I want to change it to atmospheres, okay. Use a conversion factor. 1 atmosphere is 760. So write down what I know, 740. Now I'm going to use a conversion factor. I'm going to put this on the bottom and I'm going to put 1 atmosphere because this equals 1. This is a conversion factor. So basically 740 divided by 760. So it's not quite 1 atmosphere, which makes sense because it's a little less than this atmosphere, okay? So when you need to convert, it's easy. Just remember 1 atmosphere is 760. And I'll give you a sheet with all these numbers. I don't expect you to memorize all of them. Okay, if I'm doing, what am I doing here? 740 to kilopascals. Okay, so again, I'm going to write down 740 and 101.3 kilopascals equals 760 millimeters per mercury. Sorry, I should say that right. Okay, so again, write down what I know. These is just like multiplying by 1. They equal each other. So again, now I'm going to take this times this and divide by this. And I get a number a little less than 1 because this is a little less than 1. If 760 is 1, then it should be a little less than this. Okay? So you can convert them easily. You don't have to convert too often, but again, the units that we use most often are these 3. Millimeters of mercury, atmospheres, and kilopascals. Okay, so when we're talking about atmospheric pressure, you hear this all the time, like on the news and all that. It's the total pressure exerted by gases in the atmosphere. If you think about it, the atmosphere is above us. It's what we breathe, right? But it's being pushed down. It's being exerted down by gravity, okay? Most of the atmosphere we have is right now down toward the surface because of gravity, okay? And you guys have probably heard, like if you go to Denver, you have less, the air is thinner in Denver. Well, it's up higher, okay? So the lower you go, the more atmosphere that you have, the more oxygen and whatever air you want to call it, okay? If you're talking about air, air is mostly nitrogen, N2. And oxygen is next, and then we've got all kinds of things. We've got argon, carbon dioxide, neon, and it depends on where you're at. Because remember, air is a mixture. It's a well-mixed mixture. It's a solution. But it can change. The air inside your house is probably not the same as the air outside. So because it can change its things. But these two are pretty much consistent. 78% of air is nitrogen, about 21% is oxygen, and all the rest is these little, there's water vapor and there's carbon dioxide and a lot of the noble gases, okay? All right, so if you want to measure pressure, if you're using a barometer, okay, and this was the first way they did it. They took a tube and filled it full of mercury. We don't do these anymore because people would break those tubes and play with the mercury, and mercury's not good for you. So we don't get mercury anymore in them, but I got to do it when I was a kid, and maybe that's why I'm a little bit stranger than you guys, is because we got to play with mercury. But anyway, they took the tube and they filled it with mercury and they inverted down in here. Now what happens is, this is a vacuum tube, so when air exerts pressure here, it forces the mercury up. And then they just read whatever the level is. Okay, if you're at sea level, it's 766. 760, sorry, not 66, 760. Okay, that's sea level. So if you're above sea level or below sea level, if you're below sea level, it's going to exert more pressure, so it's going to go up. If you're above sea level, okay, it doesn't exert as much pressure, so it doesn't go up as far. Okay, that's how a barometer works. Okay, the mercury will be supported or pushed up by the pressure of the atmosphere. So the more pressure you have, the higher it goes. So again, if you're below sea level, it's going to be higher than 760. If you're above sea level, it's going to be lower. Okay? The height of the column, and again, is what we use to measure. They'll have marks on it, and then you just read it. Okay? All right. So the things that pressure depends on. One of them, like I said before, is the number of molecules. The more molecules you have, the more pressure they can exert. Okay? So pressure is directly proportional to the number of gas molecules. When you increase the number of molecules, you increase the pressure. That's what they mean by directly proportional. One increases, the other increases. One decreases, the other decreases. It's that simple. Okay, so when they're talking about the number of gas molecules present, when we do formulas, they use the letter N. Okay, The temperature has to remain constant and the volume has to remain constant, because if you mess with those, then you're going to change the outcome. But if you're just looking at pressure versus number of molecules, they are directly proportional. When one increases, the other one increases. Okay? Here they're showing a half a mole of H2 gases. Its pressure is 0.5. Here we have 1 mole, okay? And the pressure increases and so on. So when you're talking about pressure, again, when you increase the number of molecules, you increase the pressure. Okay, another thing the pressure depends on is temperature. It's also directly proportional, okay? When you increase the temperature, you increase the pressure. Plain and simple. It makes sense, because if you increase the temperature, then the particles move around faster, so they're going to exert more pressure. They're going to bang in the sides more. Here, let's see, we've got, I know you can't see it and I apologize for that. Here the temperature goes from 0 to 100. So you can see here we have 2.24 atmospheres and here we have 3.06 when we increase the temperature. Okay, now most of the time when we do problems, I shouldn't say most of the time, whenever we do problems with gases, we don't use Celsius, we use Kelvin, okay, because we need absolutes. It's really easy though. You just take the Celsius temperature and you add 273 to it. So it's not hard to convert. So this would be 273 Kelvin. This would be 373 Kelvin. You just add 273, okay? So when you increase the temperature, the reason why you increase the pressure is you get more collisions, okay? They're moving around faster, so they're going to bang in the sides, so they're going to exert more pressure, okay? So there's this guy named Boyle, and his law says if you have a fixed amount of gas, in other words, the only thing we're going to look at is the temperature and the pressure. Everything else stays the same. The amount of molecules, the temp, those stay the same. But when we're talking about volume and pressure, so if we increase the pressure, we decrease the volume. And it's really easy if you think about it. Take a balloon. Okay, you got a balloon and you got so much pressure in. Squish it. You're increasing the pressure on that balloon. The volume's going to go down. You're going to make it go smaller. When you release the pressure, then it gets bigger again. So it increases the volume. So when you're talking about Boyle's law, it's inversely proportional. In other words, if you increase one, you decrease the other. And Boyle's law deals with pressure and volume. I always remember Boyle's as the pressure one because I always think of Boyle's pressure, blood pressure, you know. That's just me. You don't have to do that if you don't want to. But anyway, if you're trying to figure it out, here's the formula. The pressure of the first one times the volume of the first one equals the pressure of the second one times the volume of the second one. Okay? Okay, so if I'm trying to solve a Boyle's law problem, what I'm going to do, I got 3.5 liters of gas and its pressures change from 730 to 600. Okay, so I got volume 1, pressure 1, and I've got pressure 2. So really all I'm going to do is take this times this and divide by that. Okay? All you have to do when you're doing Boyle's law is take the two that you know and divide by the one you don't know and you'll get your answer. Okay? Here's another Boyle's law. Same deal. You would multiply those two and divide by. So you're going to take the volume and the pressure and multiply those two and then divide by 1 basically. Okay? So Boyle's law is easy. Again, you take the pressure and the volume, the two that you know, and then you divide by the one you don't know. Okay. Oh, I'm almost done with problems here. Okay. This will be our last slide because I'm at 14 minutes. So we'll get to Boyle's law. All right. So here we have nitrogen, 65 liters, and automobile, and has a pressure of, oh, we're going to do the airbag. Okay. So again, if I've got, this is the volume and this is the pressure. And if I switch the volume to this, well, how much pressure do I need? So I'm going to take 65 times 745 and divide by 25. Okay, let me see if we... Okay, so again, I take 745 times 65, multiply those two, and then I divide by 25. And that's why you get the 944. So Boyle's law problems are really simple. You multiply the two you know and you divide by the one you don't know and you'll get your answer. Okay, your unit will be whatever. It could be atmospheres, it could be millimeters or whatever. And I think I'm just about done. Okay, yep. So we'll end right there.